Welcome back to our discussion on this unit on thermodynamics, and in this today's lecture, third lecture which is in this unit, we will talk about enthalpy and heat capacity and then determination of internal energy change and enthalpy change for different processes. But before that, I just wanted to revise some part which I covered in second lecture, which are shown here in blue color. We know the total energy of a body E can be represented as K plus V plus U, where K is the macroscopic kinetic energy and V is the macroscopic potential energies of the body. K happens due to the motion of body through space, and V potential energy because of presence of field that acts on the body. And U is, we discussed in last class that U is the internal energy of the body due to molecular motions and intermolecular interactions. So, change in total energy could be represented as change of each of these energies. And if we talk about absence of any varying external field acting on system, which means delta V is 0 and system is at rest, delta K is 0, which is the case we talk about in chemistry, chemical reactions and different chemical processes. This is the scenario. Then total energy change would be represented by change in internal energy, and if the system does not interact with surroundings at all, there is no exchange of energy between system and surroundings, then which is the case for an isolated system, then the first law says, which is basically the conservation of energy, which says that energy cannot be created or energy cannot be destroyed. So, delta E is constant. So, for isolated system, when the system does not interact with surroundings or does not exchange any energy between system and surroundings, delta E, the internal energy should be constant. So, delta U should be 0. Okay. So, this is the mathematical description of first law of thermodynamics, that for an isolated system change in internal energy is 0. Now, what is internal energy? We discussed in last lecture as well. Internal energy is the energy of within the body, which is due to the molecular motions and intermolecular reactions, intermolecular interactions between the molecules present in a system. So, and also you know that internal energy, or we described in last class, it is a extensive quantity. So, if you increase the more amount of, if you add more amount of substance in a system, obviously internal energy will increase. So, for a closed system where we are talking about there is no change in amount or no change in composition in the system, internal energy can be given by the following term: this translational motion of the molecules, energy due to translational motion of the molecules, rotational energy, vibrational energy, electronic energy, and intermolecular, the energy due to intermolecular interactions between molecules. And U rest, we described this is the rest mass energy of the electrons and nuclei, which is given by m rest c square. C is the velocity of light, which is a constant term, and as we cannot get this experimentally measured. So, this absolute, as we discussed in the last lecture as well, the absolute value of U cannot be measured. We can only measure the change in internal energy experimentally. These terms are either, some of these terms could be constant for some cases, but most cases either they are, and in most cases they are function of temperature. These terms depend on temperature only. And the second term intermolecular, the energy due to intermolecular interactions will depend on the distance between the molecules, which will depends upon temperature and volume, or you can say temperature and pressure as well. So, the first term is dependent, these first 4 terms dependent on temperature, second terms dependent on temperature and pressure or temperature volume, and this is a constant term. So, we can write for a closed system, entropy can be, internal energy can be represented as a function of volume or temperature or function of pressure and temperature. Now, if we consider ideal gas or a perfect gas, then you know that there is no intermolecular interactions between molecules in case of an ideal gas or a perfect gas. Then this term will not be, it will be 0. So, the internal energy of an ideal gas would be only dependent on temperature for a closed system, of course. So, for an ideal gas closed system, internal energy will depend only on temperature. So, if we fix temperature and we change the volume or we change the pressure, the internal energy of the ideal gas will not change. Please keep it in this mind that internal energy of an ideal gas in a closed system only depend on temperature. So, U is a external extensive quantity, extensive property, and obviously, because it is a state function, if you come back to the original state, then change will be 0. So, the cyclic, for a cyclic process, change in internal energy is 0, and change in internal energy between 2 states, initial state and final state, is not dependent on path, is basically dependent only on the thermodynamic state of the initial state and the final state. So, how can you change the value of internal energy of a closed system? Obviously, by exchanging energy with surroundings. Now, what are the different ways we can exchange energy with surroundings? We talked about there are basically 2 ways, one by work exchange or by heat exchange. Now, work could be of different types, but in our or this unit we will be restricting ourselves only to the pressure volume work, or which also called expansion work or mechanical work. So, basically we now know that internal energy can be altered in a closed system. Internal energy can be altered by work or by heat exchange between system and surroundings. So, if you in a closed system, if you want to write the first law of thermodynamics in a general form, then we will write the change in internal energy in a closed system is given by Q plus W. What is Q? Q is the increase in the energy of the system. Remember, we are talking about increase in the energy of the system due to thermal exchange through diathermal wall, and W is the increase in the energy of the system due to mechanical exchange or expansion work through non-rigid wall. Obviously, if it is rigid wall, there will be no movement of the walls, no volume change, and then W will be 0. So, in both case Q and W, we are talking about increase in energy. Okay. So, the sign and W and Q are positive if system gains some energy, or the increase, there is a increase in energy of the system, and they are negative if system loses some energy or there is a decrease in energy of the system. So, please remember that W and Q are positive if the system gains some energy and negative if they loses some energy. So, when the surrounding does some work on the system, which happens in compression case, it is W is greater than 0 because system gains some energy, and if system does some work on surroundings, then it's which happens in case of expansion, then system loses some energy, W should be negative. Similarly, when a system receives some energy from heat from as a heat from surroundings, then Q is positive, and if system loses some energy to the surroundings, then Q is 0. Q is greater than less than 0 is negative. So, we look for some questions which are there in your textbook. Express the change in internal energy of the system when no heat is absorbed by the system from surroundings, but work W is done on the system, and what type of wall does the system have. Now, in this case no heat is absorbed. So, Q is 0. W is, this is the magnitude, W is the magnitude of work is done on the system. That means, system gains this W amount of energy. So, delta U in this case would be Q plus W from first law, and in this case W is positive because work is done on the system. And what type of wall this is? This is a no heat is absorbed. So, it is a adiabatic wall, and because there is a work done, so it will be a non rigid wall. So, I am assuming that it is a closed system, there is it is also a non permeable not permeable wall. In the second question, no work is done on the system. So, obviously, W is 0, but Q is the amount of heat taken out, note this term, taken out from the system and given to the surrounding. So, in this case system is losing some energy and magnitude is Q here. So, from first law, in the main equation we had Q was increase. So, in this case because it is decreasing, we will write W minus Q, which is minus Q in this case, no work is done on the system. So, in this case Q is the magnitude, and because the heat is taken out of system will lose some energy. So, instead of increase it will decrease. So, it will be a minus Q value, and the type of wall would be obviously non adiabatic because heat is getting exchanged, or diathermal, and it is a rigid wall because no work is done. In the third question, W is the amount of work done by the system, which means system is losing some energy. So, it will be minus W, and Q is the amount of heat supplied to the system, that means system is gaining energy. So, in this case W would be Q minus W, where W is the amount of work done by the system. When system is doing the work, that means it is losing some energy, and Q is the amount of heat supplied to the system. So, it will be the positive number, and obviously, this is a closed system because work is getting done and volume is getting changed. So, generally we talk about volume in case of closed system, especially in the gaseous system. We move to the second question. You just see for each process state whether Q, W and del U is positive, 0 or negative. So, this process is given, you have to tell whether what is the sign of Q, W and del U. So, that will clarify this one more time. So, combustion in a sealed container with a rigid and adiabatic wall. Now, when we are talking about rigid wall, that means W is 0, adiabatic wall Q is 0, obviously del U is 0 in this case. Combustion of benzene in a sealed container that is immersed in a water bath at 25 degree centigrade has a rigid thermally conducting wall. It has a thermally conducting wall, so which allows energy exchange as a heat, and because combustion of benzene is a exothermic reaction, heat gets generates which goes out of the system to the surroundings, which is the water bath. So, in this case system is losing some energy as a heat. So, Q would be negative, rigid. So, W would be 0. So, del E would be Q plus W. So, would be negative as well. C, adiabatic expansion of a non-ideal gas into vacuum. Adiabatic, Q is 0. Its expansion into vacuum. Expansion into vacuum, we know W is 0 and del U is 0. So, if I had expansion of the non-ideal gas other than vacuum, some constant external pressure, then because of expansion W would have been negative and del U would have been negative. So, I hope by this time you are very clear about the sign of W, Q and del U in any processes. So, next we will move to work, and in last and as I said the beginning of this lecture, that work could be of two types. One is basically the work, commonly what we are describing, the expansion work, the mechanical work or the PV work, and any other work like electrical work or magnetic work we call together as a non-expansion or additional work. But in this unit we will be only talking about PV work and mechanical work or work of expansion. So, if nothing is mentioned about the work, you have to assume that it is a PV work, it is a PV work on or you can just, if nothing is mentioned, as I said nothing is mentioned, you have to think that it is a PV work. And we talked about the how to calculate those in last lecture, that for a reversible process it is given by this expression, and because P external is infinitesimally close to the pressure of the system, and for irreversible process we write we have the expression where W is the P external Pex is the external pressure, final volume, initial volume, that we discussed in last lecture. Expansion against constant pressure, you can, so it is minus P delta V, V2 minus V1 or V final minus V initial. Free expansion, expansion against constant opposing pressure is P external is 0. So, W is 0, and for reversible isothermal process for ideal gas we have seen that this is the expression for work. Now, I will quickly ask a question and let us see whether you can solve this. So, that will be my question 3 in this lecture. So, I will take ideal gas and closed system and we consider a reversible process. So, what you have to do? You have to calculate the change in or calculate the work involved in this process, and you have to schematically draw the area which will corresponds to the work. So, this is the initial state, some temperature T, it is a isothermal condition to 1 Pascal, 10 meter cube is the volume and that temperature T. So, in this case that is my first part. So, if I want to get W, ideal gas, reversible process, isothermal condition. So, I can write nRT ln V final, which is 10 meter cube by 1 meter cube, and which will nRT is equivalent to PV for ideal gas. So, ln 10, which will give us minus 10 into 1, I will just write 10 meter cube into 2.303 or minus 23.303 joules. And if I want to draw schematically in this graph, if this x axis is volume and y axis is pressure, then if this is your 10 Pascal and this is say 1 Pascal and this is your 1 meter cube and this is your 10 meter cube, then you have this area corresponds to your work. Now, in the second part of this question, we will do the same thing. Instead of a reverse isothermal way, we will do it in two parts. Like I will take 10 Pascal 1 meter cube T, and then first do a isochoric constant volume process, take it to some other temperature, and then do a isobaric constant pressure process and take to get the this initial state and final state is same as in the last example here. This initial state is and final state is same in this case, but in earlier I did it a reversible isothermal way. In this case, we are doing in two step, isochoric and isobaric. Then what will be the work done in this case? Total work would be the work done in these two step, and first step is a constant volume process. So, it will be 0, and in second case it will be minus P V 2 minus V 1, which is 0 minus, I can remove 0, 1 Pascal 10 minus 1 meter cube gives 9 Z. You can see this is a expansion process, volume is going from 1 to 10 meter cubes, and because of expansion process system is losing some energy. So, in all the cases you are getting a negative value for your work. Now, if I draw this in P V scale, so this is your higher pressure to same volume, isochoric condition, you are getting to lower pressure, and then you are increasing to the volume. So, this area would be your work. So, in third case, I can do the other way around, 10 Pa 1 meter cube. Now, I just reverse the step. Earlier in last example I did it isochoric, isobaric. Now, in this case I am doing isobaric and followed by isochoric. So, in this case again W would be W 1 plus W 2, and this case minus 10 Pa 10 minus 1 meter cube plus this is isochoric process. So, that will be 0, which gives 90 joule. And if I want to draw this pressure volume curve, so you start from here isobaric process. So, this go to intermediate state and then bring the pressure down. So, this is your first process, second process. So, this is 1, 2. So, this would be your, this area would be your work done in this case. So, basically if you compare the three ones we just discussed. So, basically you are doing we are doing the same change from initial state 1 to state 2, but we are getting different value of work done, which shows that work done between two states is a path function. It does not only depend on the two states, but it depends how you are carrying out the changes. Just for your as a part of homework, you can solve this problem where you do the same change irreversible way in one step, and then two step, and then in infinite number step, which is basically a reversible process. And you also calculate the work done in forward direction and work done in backward direction, and you will see that again the value of work will be different as you change the process. So, that you can do in your yourself at home. So, next we will talk about enthalpy, and we started talking about enthalpy in last class. We defined mathematically enthalpy as U plus PV. These are all a state variable U P V. So, H is also a state variable or state function or state property, whatever you call. U is extensive quantity, it depends on the size of the system or mass of the system. So, H would be also extensive quantity, and again as the value of U cannot be absolute value of U cannot be experimentally determined. So, absolute value of H also cannot be determined experimentally. And again because it is a state variable. So, delta H, the value of delta H between state 1 and state 2 or initial state to final state will only depend on the value of delta H will only depends on the initial and final states. Now, we know that from first law from first law of thermodynamics we know first law that del U is given by Q plus W for a closed system. Of course, now if you talk a process which is at a process which is happening at constant volume. So, I have just like P 1, T 1, V to say P 2, T 2 and V. So, we are doing a change at constant volume, and if as we are doing at constant volume, obviously W would be 0, then del U would be the change which is happening at constant, the heat change which is happening at constant volume. Now, if the process is for a process at constant pressure, we can write generally like T 1, V 1, P 2, T 2, V 2 and P. In this case, we have seen in last class that QP, the heat exchange, can be written as QP is equal to del H. So, QV is the process is as constant volume, then Q is equals to del U, and if the process is constant pressure, then it is the Q is equals to the del H, enthalpy change. Now, if we consider a constant pressure process again, and then del H we know from definition del U plus constant pressure. So, we can write P del V, and for we know that for liquid or say solid, now this change in volume is negligibly small or very small, del V is very small for a process. So, in this case we can consider that del V is negligibly small. So, we can consider del V is 0. So, del H is equals to del U for solid and liquid. Okay. These are very close, not exactly same, but because the volume is very small. So, this we can consider these are almost close to this, but for gas, for gaseous the reactions or the process involved gases. So, the reactions or the processes which involved processes involving gaseous substances or gases, we had shown that in last lecture that del U is del N G R T. Now, we in that deriving this we consider that the gases are ideal. Okay. This we had considered. So, we will just move to next problem, and then just will it will be a question 5. So, we consider a process where we talking about this problem is given here. So, the molar enthalpy change of vaporization of water at 1 bar and 100 degree centigrade is 41 kilojoule per mole. Calculate the internal energy when these two 1 and 2, and assume the water vapor is a perfect gas. This is from your textbook. So, if you note down, so this is basically a vaporization process, and 1 mole of it is given 1 mole of water is vaporized at 1 bar at 100 degree centigrade. So, H2O liquid to H2O gas at 1 bar 100 degree centigrade, and we are talking 1 mole here, 1 mole. And in this case it is given del H for this vaporization process. We can write del vaporization H is 41 kilojoule per mole. Now, again this is a positive number, because for vaporization we have to add some or supply some heat to the system. So, the system actually gains some energy, that is the reason it is a positive number. So, we can get the other value del U from the expression we learned just now, plus del N G R T, or del U is del H minus del N G R T. We are talking about 1 mole of substance, 1 mole of water. So, this value 41 kJ per mole, that is a molar, into 1 mole of substance minus again 1 mole, delta N G is change of 1 mole, ignoring the volume of liquid. So, basically 1 mole of gas is produced into R value is 8.314 joule per mole per Kelvin into 373 100 degree centigrade, we are considering 373 K. In solving physical chemistry problem, you must be very careful about the units, and if you put units appropriately, you will get your final answer exactly the way you want, because it is a del U, which basically you are talking about energy change. So, it should give you a energy number. So, in this case it is giving you a energy. So, for and because you are doing it for 1 mole, you can write it that delta U for vaporization is 37.9 kilojoule per mole, but this is your answer. 37.9 kilojoule is the change in value of change in internal energy for vaporizing 1 mole of liquid to 1 mole of gas. So, in the second problem, you have 1 mole of water is converted to ice. So, we can write in so that is second one. So, H2O solid, again this is 1 mole, this is 1 mole, and generally it is done at generally this we are considering this is this transition is done at constant pressure. So, constant pressure condition is what we are assuming. So, del H can be considered at del U plus P del V, and as we talked earlier, that because of solid and liquid, the volume change is we are considering is negligibly small. So, in this case we will have del U is close to del U, which is 41 kilojoule for 1 mole of gas. So, you can write del U as equal to 41 kilojoule per mole as well, but your answer is 41 kilojoule. So, we talked about enthalpy, we talked about work, we talked about internal energy, and we now will talk about how to calculate the heat part, the Q, in your first law. Now, heat exchange happen exchange of heat energy happens because of, or heat exchange happens between system and surroundings because of temperature difference between system and surroundings, because of temperature difference, that we all know, we understand that if there is a temperature difference between system and surroundings, if they are brought in contact through a non-adiabatic wall, heat exchange will happen and heat will move from higher temperature to lower temperature. And we know that this heat is proportional to the temperature difference of system and surroundings, and if we consider a small change, then we can write dq, which is the small value, and which is we can write small, this is dq is for small value of q, and dt is the small value of, very small value of temperature difference. So, what is the proportionality constant? We have this proportionality constant as C, capital C. So, for the entire process we can get Q summation of integration of T1 T2 dt. If C is constant, in temperature range between T1 and T2, then we can take this out of integral, then it will be C del T, which is giving us the same value C del T. Okay. So, that is only you can write in case C is not dependent on the temperature, which will for in this unit or in your case we will consider that C is independent of the temperature range we are talking about. So, we now know that Q is C del T. This C is called heat capacity of the substance we are talking about. This is, remember, this is where this C is capital letter or uppercase, whatever you call. That is for the entire substance. Obviously, if you have more substance, this value will go up. So, this is a extensive quantity. Now, we can also write Q as, if we divide by number of moles and write C is NCM, where Cm is C by N, molar heat capacity, then N is the number of moles, then in this case molar heat capacity would be a intensive quantity. We can also express in terms of mass and small c, where C is capital C divided by M, and M is mass, and this case C is, remember we are talking about C is small letter or lower case, and we are calling this as specific heat capacity. Now, what is, how you can, what is the difference? Now, the heat exchange can happen or can be carried out in two ways. One at constant pressure, other could be a constant volume. Now, if, as we said, have you seen earlier, if the process is, if a process is at constant V, like the example we had earlier, P1, T1, V2, P2, T2, V, then we know del U is QV as W is 0. So, del U would be given by CV del T. Similarly, if the process is, process of our interest is at constant pressure, as we have seen earlier, then del H is QP. So, del H would be given by Cp del T. But if you have a general case, we have say a process, we have a general process, all three are changing. Say I have P1, V1, T1 to P2, V2, T2, then how do you get this del H and del U? Now, because del H and del U both are state variable, they do not depend on the path. So, we can break down the process into 2 steps. For example, if I want to get du, I will let me break this to this process into 2 steps, T1 to V1, T2 and some other temperature P3, and then. So, this is at constant V, and we do it next is constant T, T2, V2 and P2. So, we are reaching from state 1, if we call state 1 to state 2, we are going state 1 to state 2, but in 2 steps now. So, what will be del u then? Del u would be del u in the first step plus del u in the second step. Now, if you consider a simple case of an ideal gas, now what do you know? The ideal gas u is only function of temperature. So, if temperature is fixed, then del u would be 0, which means for the second step where temperature is constant, del u would be 0. So, del u second process would be 0 as temperature is fixed. Remember, we are talking about ideal gas. Please do not generalize this. This is only applicable for ideal gas, and del u 1 is a constant volume process, as we discussed earlier, it will be given by Cv dt. So, del u will be given by del 1 first process and second process. So, Cv del t plus 0 Cv del t. So, we can write del u is Cv del t, that is only for ideal gases, ideal gas. Do not, this expression is only valid for ideal gas. Please do not confuse, this is a general expression, and Cv is, we are talking about heat capacity at constant volume. Okay. Similarly, we can think of general process, and we can break down to a constant pressure and constant temperature process, and we can get again del H is Cp dt for ideal gas. If we can write one more time, delta u is Cv del t. These are for ideal gas, these are not for general example. Okay, this general is applicable. Now, how Cp and Cv are related? How they are related? Means which is, what is the relationship between them? If we consider 2 process, say we take a cylinder and first we consider this is a piston. First we consider that this is a fixed, so the volume does not changes, and we have supply some heat, which will, because we are supplying some heat, it will increase the energy and temperature will go up. So, here whatever heat is supplied here, this will increase the internal energy, which will increase the temperature of this of the system. But if we do the process at constant pressure, we write the same thing, but in this case this is not fixed, this is movable. Okay. So, this is movable or non rigid. Then if you supply heat, volume will expand, the gas, the volume of the gas will expand, and in result there will be volume expansion, and if volume expansion happens, you know that system is losing some energy or it is doing some work on the surroundings, and so it is losing some energy by doing work. So, this is a constant pressure process, this is a constant pressure we have applied, and this is a constant volume process. So, now you can compare that in this case constant pressure process, whatever energy you have supplied as a heat, it is increasing, it is used to utilized to increase the internal energy or the temperature of the system, plus some of which are getting lost as doing work on the surroundings. But here whatever you are adding as a heat, they are all getting utilized to increase the temperature. So, you can now compare that, because in this case if you want to increase same temperature del T in both cases, you have to supply more heat here. So, Q has to be more in this case compared to constant volume case, because part of the Q which is getting in is getting lost as the system is doing some expansion work on the surroundings. So, Cp is greater than Cv, and this is true mainly for gaseous substances, gases, because in case of gas the volume change is significant, and as we have talked earlier also that for solids and liquids, for solids and liquid generally the volume change del V is negligibly small. So, Cp is nearly same as Cv. So, this is the case for solid and liquid, but if you in true sense if you do not neglect the small volume change, then Cp would be greater than Cv, with exception where volume reduces or decreases on heating. If there are cases like water between 0 degree centigrade to 4 degree centigrade, on increasing or on heating the volume decreases, then you can get Cv less than Cp, but most and almost every case is Cp is greater than Cv. There are cases also exception, Cv is equals to Cv, like the when the volume goes through minimum. So, that is 4 degree centigrade water at 1 atmospheric pressure. So, these are exception where Cp is equals to Cv. Most cases or every cases with just few exception where Cp is greater than Cv. But in practically for solids and liquid, Cp is almost close to Cv, but for gases, for gaseous substances, we always have Cp greater than Cv. Now, for ideal gas, we will talk about ideal gas, that is the simplest case we are always talking. We can get del H is equal to del U plus del PV, del U plus del nRT. Now, for ideal gas we know del H is Cp del T, del U is Cv del T, and in this case nR del T. So, we can write from this Cp minus Cv is nR for ideal case, or Cpm, we talk about molar heat capacity, Cvm would be given by R. So, these are expressions for your ideal gas. Now, what we will do, we will go back and look at few questions to clarify just to see clear your ideas, and we will write say for each of the following processes. Well, just write a following process, and you have to get me the sign of q, w, del u and del h. So, I will write the process and you have to tell me the sign. So, one first would be reversible melting of benzene at 1 atmospheric pressure and normal melting point. So, you have to tell me what is the value of q, w, del u and del h. The melting process requires heat in the system. So, q must be greater than 0. This is a constant pressure process at 1 atmospheric pressure. So, q is q p, which is equals to del h. So, del h equals to 0. Now, in this case on melting volume increases. So, del v is positive, even though it is very small, but it increases, expand. So, w would be minus p del v is positive. So, w would be negative in this case, and del u is q plus w. Now, as I said, this is a solid. So, w is negligibly small compared to q. So, you can ignore q in this case. So, at q is positive, del u should be positive. So, that is the first question example. In the second example, we will do the same thing, but for ice, reversible melting of ice at 1 atmospheric pressure 0 degree centigrade. Again, you have to find sign of q. Again, for melting you have to supply heat. So, q is greater than 0 and it is a constant pressure process. So, q p is del h greater than 0. Now, in this case on melting at 0 degree centigrade 1 atmosphere, actually volume drops. So, in this case w is minus p del v. So, w should be a positive number, because the volume comes down, volume decreases. So, del u is a positive, the w is a positive quantity, but very small, as we talked about solid and liquid. So, because it is very small, so we can consider del u is equal to q plus w, and this is small. So, the sign of w should be, del u should be same as q. So, del u should be greater than 0. We will talk about the third example. Reversible isothermal expansion of an ideal gas. Now, isothermal reversible expansion. When we talk about expansion, del v is greater than 0. So, w is less than 0. Ideal gas isothermal. So, del T is 0, and when del T is 0, we know for ideal gas del E, del H is 0, del U is 0. Del U is 0, which is q plus w, and w is less than 0. So, q must have to be greater than 0. So, what we will do, we will stop in this class now. I will give you few more this type of problem in the next class, and next class we will talk about how to determine the values of del H and del U experimentally, and then we will talk about del H for different processes.